Hello everyone and welcome to the OneClass channel. My name is Donna and I'm a recent master's graduate from the Material Science program from the University of Ontario Institute of Technology, also known as Ontario Tech University. So today we're going to go over some commonly asked questions in chemistry at the high school, college, and university level. So if you needed any help with homework or with tutoring, then check out the links in the description below. Now let's just get started on our set of questions for today's session. Okay, so question 1. A chemistry student needs to standardize a fresh solution of sodium hydroxide. Carefully weighs out 365 milligrams of oxalic acid, a diprotic acid that can be purchased inexpensively in high purity, and dissolves it in 250 milliliters of distilled water. The student then titrates the oxalic acid solution with his sodium hydroxide solution. When the titration reaches the equivalence point, the student finds he has used 83 milliliters of sodium hydroxide solution. What is the molarity of the student's sodium hydroxide solution? Round your answer to 3 significant digits. Okay, so let's first write out the titration of oxalic acid with sodium hydroxide. So they gave us the chemical equation for oxalic acid, which was H2C2O4. And this was reacted with sodium hydroxide, which is NaOH. And this titration produces water. I have to write at a slant now. Plus sodium ions and C2O4 ions. Okay, so now we just have to balance this equation. So let's look at our carbons. They're balanced. Our sodium's balanced. Our oxygens, there's also 5 oxygens on each side. But if we look at our hydrogens, there's 3 hydrogens on our reactant side and only 2 hydrogens on our product side. So I'm just going to put a 2 in front of H2O. So now there's 4 hydrogens, and also there are 6 oxygens on our product side. So if I put a 2 in front of NaOH, that balances out both my hydrogens and my oxygens. But now I just need to put a 2 in front of the sodium ion. So now we have a balanced chemical equation. So the first step is to find the number of moles of oxalic acid that reacted with, or that is just in solution, I suppose. So first let's find the molar mass. So the molar mass of oxalic acid, we would need all the individual molar masses of the atoms involved, so like hydrogen, carbon, and oxygen, but they can just be found on your periodic table. So it's going to be 2 times the molar mass of hydrogen, plus 2 times the molar mass of carbon, plus 4 times the molar mass of oxygen. So the molar mass of hydrogen is 1.01 grams per mole. And for carbon, it's 12.01 grams per mole. And lastly, oxygen is 15.99 grams per mole. Okay, so if we add all these values up, we get a molar mass of oxalic acid, which is 90.03 grams per mole. So now we just have to find number of moles of oxalic acid. So number of moles can be found by dividing mass over molar mass. So we know the mass of oxalic acid was 365 milligrams, but I'm just going to convert it to grams because our molar mass is in grams per mole. So 0.365 grams is the same as 365 milligrams. So now our units for grams should cancel out, and our moles will be our main unit, and you get 4.05 times 10 to the negative 3 moles. Okay, so step 2 is to use mole ratios to find the number of moles of NaOH. So we know that our moles of oxalic acid was 4.05 times 10 to the negative 3 moles. And if we look at our balanced equation, then we can see that 1 mole of oxalic acid reacts with 2 moles of NaOH. So we need to multiply by 2 and we can show the ratio. And now you can see our moles of oxalic acid cancel out, and we're left with our moles of sodium hydroxide, which is 8.1 times 10 to the negative 3. So now step 3 is to calculate the concentration. Calculate the concentration of sodium hydroxide. Okay, so we know that concentration is equal to the number of moles over volume. So we found our number of moles in the previous step, which was 8.1 times 10 to the negative 3. And the volume of sodium hydroxide was given in the question. So he used 83 milliliters of sodium hydroxide to react with the oxalic acid. So I'm going to convert 83 milliliters to liters, just so that our value will be, our final answer will be in moles per liter. So 0.083 liters. And if we divide the two, we get 0.0976 moles per liter. This is our final concentration. So the junior tutor said that oxalic acid is a diprotic acid, and its titration with sodium hydroxide is expressed as the following. Yep. So they found the molar mass of oxalic acid, and then they found the number of moles of oxalic acid, 0.00405. Yep. And then they used the mole ratios to find the moles of sodium hydroxide, and from there we're able to calculate the concentration, and they got the same answer. So this solution is correct. Okay, so question number 2. A boron atom has 4 atomic orbitals in the second period, n equals 2. These orbitals are s, px, py, and pz. What hybrid orbitals would be made from these atomic orbitals, and how many hybrid orbitals would be made? Okay, so first let's write out the electron configuration of boron. So let's look up a periodic table that has all of the different orbitals sectioned out. And then starting from hydrogen, we just move left to right across the periodic table until we get to our desired element, which is boron, just found here. And then we just write the row number and then the block letter. And then using superscripts, show how many electrons are in each orbital. So starting from hydrogen, we write 1s2, and then onto the next row is 2s2. And then when we get to the boron, we just write 2p1. And then I'll also just sum up what the junior tutor said already. They have 4 atomic orbitals, which are s, p, x, py, and pz. So in general, we'll have 3 hybrid orbitals. Of sp2, with an unhybridized p orbital. So we basically need to go through all the different options of combinations of sp2 orbitals and an unhybridized p orbital. So for example, we can have an s, px, py hybrid orbital and an unhybridized pz. Another combination is s, px, pz, and an unhybridized py. And lastly, we can have an s, py, pz, and an unhybridized px. Okay, so therefore 3 hybrid orbitals can be made of sp2. Okay, so the junior tutor said that boron has an atomic number of 5 with an electron configuration of 1s2, 2s2, 2p1. It has a valence electron of 3, means it can accommodate 3 bonds. Therefore, it can form a total of 3 hybrid orbitals of sp2 with an unhybridized p. So they have spx, spy, unhybridized z, spx, pz, unhybridized py, and spz, py, unhybridized px. Okay, so this solution is correct. Okay, question number 3. What are the Lewis structure and Vesper model of CHO2-? Okay, so when writing out the Lewis structure, we first need to find the total number of valence electrons for this ion. So let's calculate it. So carbon has 4 valence electrons, hydrogen has 1, oxygen has 6, and there are 2 oxygen atoms, so we multiply this by 2. And lastly, this ion has an overall -1 charge. So we know we need to add an additional electron to this electron count. So if we add all these up, we should get 18 valence electrons. So now let's draw carbon as our central atom. And then I'm just going to draw out single bonds to 2 oxygens and 1 hydrogen. So notice that carbon doesn't have a full octet yet, so I'm going to make one of these oxygens double bonded, and then I'm just going to fill in all the valence electrons, and then we can count out all the electrons to see how many I've drawn so far. So each bond contains 2 bonding electrons, and there are 10 in the form of lone pairs. So we have our 18 electrons drawn in this structure. So now at the bottom, I'm just going to calculate the formal charge of all of my atoms just to see which one carries that negative charge. So the equation for formal charge is the number of valence electrons minus the number of non-bonding electrons. So these are all the electrons that don't participate in the bonding, such as the ones in the lone pair. And this will be minus the number of bonding electrons divided by 2. So first, let's find the formal charge of hydrogen. Hydrogen has 1 valence electron. There are 0 lone pairs, and there's only 1 bond to hydrogen, so there's 2 bonding electrons divided by 2. So it has a formal charge of 0. For carbon, there are 4 valence electrons, 0 lone pairs, and there's 4 bonds to hydrogen, so 8 bonding electrons divided by 2. Also get 0. And now let's calculate the formal charge of one of our oxygens, the one that has a double bond. So oxygen has 6 valence electron. It has 4 non-bonding electrons. And because there's a double bond, there are 4 bonding electrons divided by 2. So the double bonded oxygen also has a formal charge of 0. So now let's do the single bonded oxygen. Oxygen has 6 valence electrons, and there are 6 non-bonding electrons, and there's 1 bond to the oxygen, so we have 2 bonding electrons divided by 2. So we can see here that this oxygen will carry the negative charge. So I'll just label that in. And now the question also wants us to determine the Vesper model of this ion. So we need to look at our central carbon atom and take note that it has 0 lone pairs and 3 bonded atoms. So now I just need to look up a Vesper chart to help us find out its molecular shape and electron geometry. So when our central atom has 3 bonded atoms and 0 lone pairs, you can see it has a trigonal planar molecular shape and electron geometry. I'm just going to write trigonal planar. You can see that our carbon is sp2 hybridized, and the bond angles in between atoms are around 120 degrees. Okay, so now let's see what the junior tutor said. In order to find the Lewis structure, we need to determine first the total valence electrons that are participating in the bond formation. So they also got 18. The additional electron comes from the excess from the ion that is represented by its charge, which is -1. After finding the total valence electrons, pick the least electronegative atom. So that would be hydrogen, but since hydrogen can only form 1 bond, then carbon would make sense to being the central atom. And then you complete the total valence electrons by placing lone pairs on atoms with an incomplete octet. So CHO2- has 3 electron bonding groups and no lone pairs around the central atom, which corresponds to a trigonal planar structure. Yep, so this solution is correct. Okay, so question number 4. Why was the chromatography column kept at 60 degrees during thermal desorption of the extraction fiber? So it sounds like somebody did a lab and they needed to desorb a certain analyte from the fiber, or from the chromatography column. Why couldn't I just say that? Okay, so temperature of 60 degrees. So this is a little raised, but the reason why we would want to change the temperature of the column is because you may get better separation peaks when doing chromatography. So the point of chromatography is you kind of start off with a mixture of different analytes, and then when we put it through this column, it'll separate into its different components, and there are different factors that can separate into different components, like differences in polarity or differences in size even. So then you end up getting all your separate species, and you can kind of see where they get separated. So I'm just using random colors to show that some of them get eluted at the top. And it also depends on if your column is polar or non-polar, or if the solution that you run through the column is polar or non-polar. And then this will separate all your peaks. So when you have a temperature of 60, then you may get better separation, and sometimes you can even go higher in temperature as well to elute some of the larger molecules. So the junior tutor said that most chromatography columns are operated between 60 to 70 degrees Celsius. The reason behind this is that the higher the temperature, the faster is the elution of the samples, which might give poor retention time and separation. Keeping the temperature at 60 degrees gives better separation peaks, which are desired when doing chromatography. Yep, so this solution is correct. So not only does a higher temperature separate your peaks, but it can also make the reaction go a little faster. Okay, so question number 5. What mass of methanol must be added to 2.5 moles of ethanol in order to produce a solution containing equal numbers of molecules of the two substances? So let's find out how many molecules of ethanol there are. And I'll just use ETOH, which means ethanol. So to find the number of molecules, we start off with the moles of ethanol, which is 2.5 moles, and we multiply this by Avogadro's number. Avogadro's number is 6.022 times 10 to the 23 molecules per mole. So this is how you find the number of molecules when you're just given moles, and you end up with 1.51 times 10 to the 24 molecules of ethanol. So the question says we want to produce a solution containing equal numbers of molecules of the two substances. So notice that if we wanted to have the same number of molecules of the two substances, then we need the same number of moles. So if I were to work backwards and try to find out how many moles of methanol I need, that means I still would need 2.5 moles. So I'm just going to say, therefore, 2.5 moles of methanol are needed. So for step 2, we need to find the mass of methanol. So when calculating mass, all we need to do is multiply the number of moles by the molar mass. So let's find the molar mass of methanol, maybe just down here. So methanol has the structure of CH3 and an OH group. So you can see there's 1 carbon, 4 hydrogens, and 1 oxygen. So just by going to our periodic table, we can find the different molar masses of these atoms. So it's going to be the molar mass of carbon plus 4 times the molar mass of hydrogen plus the molar mass of oxygen. So carbon's molar mass is 12.01 grams per mole. Hydrogen is 1.01 grams per mole. And oxygen is 15.99 grams per mole. So if we add all these values up, you should get a molar mass of methanol to be 32.04 grams per mole. So now we can plug this in to our number of moles equation. So we need 2.5 moles. And we calculated the molar mass to be 32.04 grams per mole. So if we multiply these two, we need 80.1 grams per mole. Okay, so that's part A of this question. And for part B, it says, assuming no chemical reactions occur, what is the total number of molecules present in the solution? So we know that we have the same number of molecules for both ethanol and methanol. So we just need to multiply 1.51 times 10 to the 24 by 2. And you should get 3.012 times 10 to the 24. Okay, so now let's see what the junior tutor said. Consider the following values. So the molar mass of methanol is 32.04 grams per mole, and the molar mass of ethanol is 46.07. They also have Avogadro's number, and then they found the number of molecules for ethanol, and they found that they just needed the same number of moles of methanol, and then they calculated for mass by multiplying 2.5 by the molar mass of methanol, and they also got 80.1 grams. For total molecules, they just added those two values up and also got 3.012 times 10 to the 24. Okay, so this solution is correct. Okay, so question number 6. Why does glucose 6-phosphate, why does it must be isomerized to fructose 6-phosphate in glycolysis? Okay, so let me show out this reaction scheme, starting with glucose 6-phosphate. So just bear with me while I write out the linear structure of glucose 6-phosphate. So notice that it's glucose in its linear form with a phosphate ion on the 6th carbon. So this is glucose 6-phosphate. And like the question mentioned, this molecule is isomerized to fructose 6-phosphate. So let me show the isomerization using those arrows. And then I'll also draw the structure of fructose 6-phosphate. So with fructose 6-phosphate, our alcohol group is now on carbon 1. And there's now a ketone on our 2nd carbon. But the rest of the molecule is the same. And this is fructose 6-phosphate. Okay, so now I'm just going to show out the reaction that occurs right after this. So an ATP comes in and adds an additional phosphate ion to that carbon 1. And because it is now an alcohol group, we can easily attach a new phosphate to this carbon. So it's kind of cut out. Let me just... So that's a double bonded oxygen at the top. And you can see that this ketone is here. And then the rest of the molecule looks the same. And the name of this molecule is fructose 1,6 bisphosphate. Okay, so reason why we want to convert glucose 6-phosphate, or the reason why we want it to be isomerized to fructose 6-phosphate is so that it can get converted get phosphorylated or phosphorylated then the step after that, then it can be easily split via a reverse aldol condensation. Because in the next steps of glycolysis, this big molecule will split into two smaller ones, and each of them will contain a phosphorus ion. Okay, so let's see what the junior tutor said. They said that the isomerization of glucose to fructose helps in the breakdown of glucose into 3 carbon chain molecules, since an aldolase requires an adjacent carbonyl atom in the cleavage site. This helps ensure that the carbon will be split into 2 separate 3 carbon chain molecules and would undergo the same process after the cleavage. So notice that after this cleavage, then you would get the 3 carbon chain molecules, and the aldolase requires an adjacent carbonyl atom, so in this case it is this carbon right here. So this solution is correct. Okay, so question number 7. What is the freezing point of an ethanol solution that boils at 80 degrees Celsius? And then they just have the data for ethanol. Kf is 1.99 degrees Celsius over molality. Tf is negative 117.3 degrees Celsius. Kb is 1.22 degrees Celsius over molality. And Tb is 78.4 degrees Celsius. Okay, so let's write down everything that we know. We know the Kf value. We also know the freezing point of the pure solution. Kb and the boiling point of the pure solvent. So step 1 is to find the molality, which is M. So first let's recall the boiling point evaluation equation. Or boiling point, elevation. Which is equal to delta TB is equal to KB times M, which is molality. So delta TB can also be broken down to the boiling point of your solution minus the boiling point of your pure solvent. So we know from the question that it boils at 80 degrees Celsius. So the solution boils at 80 degrees Celsius. And we know that the pure solvent boils at 78.4 degrees Celsius. We know our KB value is 1.22 degrees Celsius over M. And then we just need to solve for this molality. So if we do the math, you end up getting 1.31 M. Okay, so now for step 2, I'm just going to write the equation for freezing point depression. So similar to the boiling point elevation, it's going to be delta TF is equal to KF times molality. And again, delta TF can be broken down to the freezing point of your pure solution minus the freezing point of your solution. And this is equal to KF times M. So we know the freezing point of our pure solvent is negative 117.3. And we're trying to solve for our freezing point of solution. We know our KF value is 1.99 degrees Celsius over M. And we found M in the previous step to be 1.31. So now, if we just solve for the unknown, we get a freezing point of the ethanol solution to be equal to negative 119.91. Okay, so now let's see what the junior tutor said. Consider the following equations: the boiling point elevation and the freezing point depression. And then they define what each of the variables mean. Okay, so that's helpful. And then given the boiling point of the solution, we can find the, I think they mean molality of the solute, morality. And they got 1.31 meter. Molality. Now they use the freezing point depression equation to solve for the freezing point of solution, and also got negative 119.91 degrees Celsius. So this solution is correct. Okay, so question number 8. The melting point of ammonia is negative 77.7 degrees Celsius, and its boiling point is negative 33.34 degrees Celsius. In what physical state does ammonia exist at negative 38 degrees Celsius? So first let's recall the melting point definition. This is the temperature where a solid converts to a liquid. And for boiling point, this is the temperature where your liquid turns to a gas. Okay, so now let's look at ammonia's melting points and boiling point. And then I'll just break down 3 different states: solid to a liquid, then to a gas. And we know that its melting point is negative 77.7 degrees Celsius, and we know its boiling point is negative 33.34 degrees Celsius. So when the temperature is negative 38, this is found kind of in the middle, maybe closer like this. And we need to know what physical state does ammonia exist at this temperature. So we can see that it is a bit cooler than when it's a liquid, but it didn't reach its boiling point yet to turn into a gas. So therefore, at this temperature, ammonia is a liquid. So the junior tutor said that melting point is the temperature where a compound transitions from a solid into a liquid, and vice versa, while the boiling point is the temperature when a compound transitions from a liquid to gas, and vice versa. Negative 38 degrees Celsius is past the boiling point of ammonia, but before the melting point, which means that the state of ammonia lies between the two. Intersection between boiling point and melting point is a liquid, which in melting point transforms into a solid and in boiling point transforms into a gas. Therefore, the physical state of ammonia at negative 38 degrees is a liquid. Okay, so this solution is correct. Okay, so question number 9. Consider the reversible reaction. We have N2O4 as a gas. And it's reversible. And it can form NO2 gas. Part A is to calculate the equilibrium constant, A, for the reaction if the equilibrium concentration for the reactants and products are the following: 7.5 moles per liter, 1.3 moles per liter. Okay, so let me write the general K expression, where K will be equal to our products to the power of its coefficient in the balanced equation. So in this case, it's 2, divided by the concentration of our reactants. And it would also be to the power of its coefficient, but in this case, it's just 1, so we don't need to write in that exponent. So now that we know the K expression, we can sub in the concentrations that they give us in the question. So the concentration of NO2 was 1.3, and the concentration of N2O4 was 7.5. So now this gives us an equilibrium constant of 0.225. So this was part A. And now for B, what is the description of the reaction at equilibrium? So since our K value is less than 1, this tells us that reactants are favored. At equilibrium. Okay, so now let's see what the junior tutor said. For part A, in calculating the equilibrium constant of a reaction, the concentration of products is divided by the concentration of the reactants. Also, each concentration is raised to a certain power that depends on their numerical coefficient in a balanced chemical equation. Okay, so we have our balanced reaction. They have the same K expression and also got an equilibrium constant of 0.225. For part B, a less than 1 equilibrium constant means that the reactants are favored in the reaction. As seen in the equilibrium concentrations, the reactants have a greater concentration than the product. This indicates that the reaction proceeds towards the reactants rather than the product. Okay, so this solution is correct. Great answer. Okay, so those are all the questions for today's session. And if you enjoyed today's Q&A and you'd like to be notified of when we do this next, please hit the subscribe button and notification bell below. And if you'd like to submit a question of your own, then check out the links in the description. And also, if you enjoyed today's video, you can leave it a thumbs up and a comment, or you can share it with your friends and classmates if they needed any help with chemistry. This has been Donna from OneClass, and I hope to see you soon. Bye.